Welcome to this video. Today, we'll be tackling an interesting coding problem from LeetCode, problem number 238, product of array except self. This problem is a common interview question and a great test of your problem solving and optimization skills. Let's dive in and explore how to solve it. In this problem, you are given an integer array called nums, and your task is to return another array, answer, where each element at index I is the product of all elements in nums except the one at index I. However, there's a catch: you cannot use division to compute the result. Additionally, the solution must be efficient, running in O(n) time, where n is the size of the input array. The input is a single integer array nums of size n, and the output is another integer array answer, also of size n, where each element satisfies the described condition. To make this clearer, let's walk through some examples to understand what the output looks like for specific inputs. Consider the first example. If the input array is nums equals 1, 2, 3, 4, the output array would be 24, 12, 8, 6. Let's break this down. For index 0, we exclude the value nums, 0, and calculate the product of the remaining elements, 2 asterisk 3 asterisk 4, which equals 24. For index 1, we exclude nums, 1, and calculate 1 asterisk 3 asterisk 4, resulting in 12. Similarly, for index 2, the product of all elements except nums, 2, is 1 asterisk 2 asterisk 4, which gives 8. Finally, for index 3, the product of all elements except nums, 3, is 1 asterisk 2 asterisk 3, which equals 6. As you can see, the challenge is to compute these results efficiently without simply iterating and multiplying for every index. Now let's examine another example. For the input nums equals -1, 1, 0, -3, 3, the output is 0, 0, 9, 0, 0. Here, the presence of 0 in the array makes the calculations interesting. For index 0, the product of all elements except nums, 0, is 1 asterisk 0 asterisk -3 asterisk 3, which results in 0 because of the 0. Similarly, for index 1, the product is -1 asterisk 0 asterisk -3 asterisk 3, which also results in 0. However, for index 2, where nums, 2, is 0, the product of the other elements is -1 asterisk 1 asterisk -3 asterisk 3, which equals 9. The remaining indices also result in products of 0 since they include the 0 in their calculations. This highlights the need to carefully handle zeros in the array. Finally, consider a simpler example with only two elements, nums equals 2, 3. The output here is 3, 2. For index 0, the product of all elements except nums, 0, is simply 3, and for index 1, the product of all elements except nums, 1, is 2. This straightforward case shows that the solution must work even for the smallest valid size of the input array. Additionally, there are some constraints to keep in mind for this problem. The array length will always be between 2 and 10^5, each element of the array will be in the range -30 to 30, and the product of any prefix or suffix of the array is guaranteed to fit within a 32-bit integer. Edge cases to consider include arrays with zeros, arrays with negative numbers, and arrays with only two elements. Handling these cases correctly is crucial for a complete solution. To tackle this problem, let's first consider a brute force approach. The idea here is straightforward. For each index in the array, we calculate the product of all elements except the one at that index. This can be done by initializing a product variable for every index and iterating through the array to multiply all elements except the current one. While this method is conceptually simple, its major drawback is efficiency. The nested loops result in a time complexity of O(n squared, which becomes impractical for large arrays. Additionally, while the space complexity is minimal, this approach is far too slow to be a viable solution for competitive programming or real-world applications. Clearly, we need a better strategy. One such alternative involves using prefix products, which brings us to our optimized approach. Here, the key insight is to split the product calculation into two components: the product of all elements to the left of the current index and the product of all elements to the right of it. These two components can then be multiplied together to get the desired result for each index, all while avoiding division, which is not allowed in this problem. By leveraging the concept of prefix products, we can achieve a time complexity of O(n). The process involves creating two auxiliary arrays, left and right. The left array stores the cumulative product of all elements to the left of each index, while the right array does the same for elements to the right. Once we have these two arrays, we can multiply the corresponding values in left and right to compute the result for each index in the output array. To further optimize space, we can eliminate the use of separate left and right arrays by utilizing the output array itself for intermediate calculations. This way, we compute the left products in a first pass, and then traverse the array in reverse to incorporate the right products directly into the output array. This approach not only reduces space complexity to 0, but also maintains the clarity and efficiency of the algorithm. The single-pass optimization is particularly elegant because it combines efficiency with minimal space usage. By storing the left products directly in the output array during the first pass, we avoid the need for an extra left array. Then, during the second pass, we compute the right products while simultaneously updating the output array with the final results. The time complexity remains O(n), as we still perform only 2 linear passes through the array. Meanwhile, the space complexity is reduced to O(1), not counting the output array, since no additional arrays are required. This strategy was chosen because it strikes a perfect balance between clarity, efficiency, and space optimization. The key insight here is recognizing that the left and right products can be computed sequentially without the need for additional storage, making the algorithm both elegant and practical for large inputs. With any optimization, there are trade-offs to consider. While the single-pass solution is highly efficient, it does require careful handling to ensure that intermediate values in the output array are not overwritten prematurely during the second pass. This can make debugging slightly more challenging compared to the two-pass method with separate left and right arrays, as those approaches keep computations logically distinct. However, the benefits of reduced space usage and improved efficiency outweigh these minor complexities. In conclusion, the single-pass optimized approach is the best choice for solving this problem. It adheres to the constraints, avoids division, and minimizes both time and space complexity. By leveraging sequential prefix calculations, we achieve an elegant and performant solution that scales well for large inputs. To solve this problem, we need to compute a new array where each element is the product of all other elements in the input array except itself. However, we're restricted from using division, and the solution must be efficient, ideally with a time complexity of O(n). A brute force approach, where for each index we multiply all elements except the one at that index, would involve nested loops and result in a time complexity of O(n squared). We can do better by breaking the problem into manageable pieces. First, we calculate prefix products, which store the cumulative product of elements to the left of each index, and suffix products, which do the same for elements to the right. By combining these two arrays, we can efficiently compute the desired result for each index in linear time. Now, let's delve into the computation of suffix products and how we use these intermediate results to calculate the final output. The suffix array works similarly to the prefix array but considers elements from the right. We initialize the last value of the suffix array to 1 because there are no elements to the right of the last index. Then, we iterate backward through the array, calculating the cumulative product of all elements to the right of each index. With both the prefix and suffix arrays in place, we combine them to compute the final output. For each index, the product of the prefix and suffix values gives the result for that index, since together they represent the product of all elements except the one at that position. Once this computation is complete, we return the output array. There are a few key insights that make this algorithm particularly efficient. First, avoiding division is crucial since division can cause issues with zeros in the array or may simply be disallowed. Instead, computing prefix and suffix products ensures accuracy and bypasses these limitations. Second, we can optimize space by reusing the output array to store intermediate results, reducing the space complexity from O(n) to O(1), aside from the output itself. This makes the algorithm much more space efficient. Finally, we must handle edge cases, such as arrays with a single element, where the result is simply 1, or arrays containing zeros, which won't break the algorithm since we never divide. The choice of data structures is also essential. The input array, and the prefix, suffix, and output arrays each serve a specific purpose in organizing and processing the data. Analyzing the complexity, this approach has a time complexity of O(n). Calculating the prefix and suffix products each takes O(n), and combining them to compute the output also takes O, n. As for space complexity, the initial implementation uses O, n, space due to the separate prefix and suffix arrays. However, this can be optimized to O, 1 additional space by reusing the output array. Let's go through a concrete example to see how this works. Consider the input array 1, 2, 3, 4. First, we compute the prefix products. Starting with an initial prefix array of 1, 0, 0, 0, we calculate each cumulative product. Prefix 1 becomes 1, prefix 2 becomes 2, and prefix 3 becomes 6, resulting in a final prefix array of 1, 1, 2, 6. Next, we compute the suffix products. Starting with an initial suffix array of 0, 0, 0, 1, we work backward through the array. Suffix 2 becomes 4, suffix 1 becomes 12, and suffix 0 becomes 24, giving us a suffix array of 24, 12, 4, 1. Now, the output array is computed by multiplying the corresponding prefix and suffix values. For index 0, the output is 24, for index 1, it's 12, for index 2, it's 8, and for index 3, it's 6. This gives us the final output array, 24, 12, 8, 6, which is the desired result. This example demonstrates how the algorithm efficiently combines prefix and suffix products to compute the output in linear time. To further optimize the algorithm, we can eliminate the need for separate prefix and suffix arrays altogether. Instead, we compute the prefix products directly in the output array during the first pass. Then, during a second pass, we traverse the array in reverse to calculate the suffix products while updating the output array in place. This approach maintains the same time complexity of O, n, but reduces the space complexity to O, 1, as we no longer need additional arrays to store intermediate results. By leveraging this optimization, we make the solution not only efficient but also more space-conscious, which is especially beneficial for larger input arrays. This Python implementation solves the problem using a two-pass approach to calculate the product of all elements except the current one, without using division and in O, n, time complexity. 1. Initialization. We start by creating an output array of size n initialized to 1. This array will store the results. We also initialize left_product to 1 for calculating the cumulative product of elements to the left of each index. 2. First pass, left products. We iterate over the input array nums from left to right. For each index I, the value of output, I, is set to left_product, which initially starts at 1. Then, left_product is updated by multiplying it with nums, I. This ensures that output, I, contains the product of all elements to the left of index I. 3. Second pass, right products. After the first pass, we initialize right_product to 1 for calculating the cumulative product of elements to the right of each index. We then iterate over nums from right to left. For each index I, we multiply the value and output, I, by right_product. Then, right_product is updated by multiplying it with nums, I. This ensures that output, I, now contains the product of all elements except the one at index I. For return, finally, the output array is returned as the result. This approach avoids using extra space for additional arrays, as we reuse the output array, and achieves optimal time complexity. The algorithm effectively calculates the left and right products in two separate passes, ensuring correctness and efficiency. This is the Java implementation of the product of array except self problem, replicating the logic from the Python solution. The algorithm calculates the product of all elements except the current one without using division. It uses two passes, one to calculate the left product and another for the right product. Key differences include explicit type declarations, array initialization, and Java syntax for loops and arrays. Let's start by looking at the input array, which is 1, 2, 3, 4. The length of this array, n, is 4. We also initialize an output array with all elements set to 1, so it starts as 1, 1, 1, 1. Additionally, we initialize a variable called left_product to 1. Now, we begin computing the left products by iterating through the input array from left to right. At index 0, we set output 0 to left_product, which is currently 1, and then update left_product by multiplying it with nums 0, which is 1. So, left_product remains 1. At index 1, we again set output 1 to left underscore product, which is still 1, and then update left underscore product by multiplying it with nums 1, giving us 2. At index 2, output 2 is set to 2, the current value of left underscore product, and left underscore product is updated to 6 by multiplying it with nums 2. Finally, at index 3, output 3 is set to 6, and left underscore product becomes 24 after multiplying it with nums 3. The intermediate output array at this stage is 1, 1, 2, 6. Next, we move on to compute the right products and combine them with the left products to get the final result. We initialize another variable, right underscore product, to 1. Now, we iterate through the input array from right to left. At index 3, we multiply output 3, which is 6, by right underscore product, which is currently 1. This keeps output 3 as 6. We then update right underscore product by multiplying it with nums 3, resulting in 4. At index 2, output 2, which is 2, is multiplied by the updated right underscore product 4, giving us 8. Then, right underscore product is updated to 12 by multiplying it with nums 2. At index 1, output 1, which is 1, is multiplied by right underscore product 12, resulting in 12. Right underscore product is then updated to 24 after multiplying it with nums 1. Finally, at index 0, output 0, which is 1, is multiplied by right underscore product 24, giving us 24. Right underscore product is updated once more, but at this point, we have our final output array 24, 12, 8, 6. Now, let's look at another example with the input array 2, 3, 4, 5. Once again, we initialize the necessary variables. The length of the array, n, is 4, and the output array starts as 1, 1, 1, 1. We also set left underscore product to 1. To compute the left products, we iterate through the array from left to right. At index 0, output 0 is set to 1, the current value of left underscore product, and left underscore product is updated to 2 by multiplying it with nums 0. At index 1, output 1 is set to 2, then left underscore product is updated to 6 by multiplying it with nums 1. At index 2, output 2 is set to 6, and left underscore product becomes 24 after being multiplied by nums 2. At index 3, output 3 is set to 24, and left underscore product is updated to 120 after multiplying it with nums 3. At this stage, the intermediate output array is 1, 2, 6, 24. Now for the right products, we initialize right underscore product to 1. At index 3, output 3, which is 24, is multiplied by right underscore product, keeping it as 24. Right underscore product is then updated to 5. At index 2, output 2, which is 6, is multiplied by right underscore product, resulting in 30. Right underscore product is updated to 20. At index 1, output 1, which is 2, is multiplied by 20 to get 40, and right underscore product is updated to 60. Finally, at index 0, output 0, which is 1, is multiplied by 60, giving us 60. The final output array for this example is 60, 40, 30, 24. In the last example, the input array is 5, 6, which has a length of 2. The output array is initialized as 1, 1, and left underscore product is set to 1. For the left products, we iterate through the array from left to right. At index 0, output 0 is set to 1, the current value of left underscore product, and left underscore product is updated to 5 by multiplying it with nums 0. At index 1, output 1 is set to 5, and left underscore product becomes 30 after multiplying it with nums 1. The intermediate output array is now 1, 5. For the right products, we initialize right underscore product to 1. At index 1, output 1, which is 5, is multiplied by right underscore product, keeping it as 5. Right underscore product is updated to 6. At index 0, output 0, which is 1, is multiplied by right underscore product, resulting in 6. Right underscore product is updated to 30, but the calculation is complete at this point. The final output array for this example is 6, 5. The time complexity of this solution can be understood by analyzing its main steps. First, initializing the output array requires iterating through the input array to create a new array of the same size. This operation takes n time. Next, we have the first loop, where we compute the left product for each element. Here, we iterate from left to right, updating the output array and the left product variable in each step. Since this loop processes each element exactly once, it also has a time complexity of n. Finally, we have the second loop, which calculates the right product and finalizes the output array. This loop iterates from right to left, again processing each element once and performing constant time operations like multiplication and assignment. Therefore, this loop also contributes n to the time complexity. When we combine these steps, the total time complexity of the algorithm becomes n. The total time complexity can be expressed as n plus n, which simplifies to n. Now, let's consider the space complexity. The primary memory usage comes from the output array, which stores the result for each element in the input array. Since the output array has the same size as the input array, it requires n space. Additionally, we use two variables, left_product and right_product, to store intermediate results during the left and right product computations. These variables are scalar values, so they require one space each. Importantly, no other temporary data structures or arrays are used, meaning the algorithm has no extra space overhead beyond the output array and these two variables. Adding these components together, the total space complexity is n for the output array plus 1 for the two variables, which simplifies to n. Now, let's compare this optimized approach to a naive solution. In a brute force method, for each element, we would compute the product of all other elements using nested loops. This results in a time complexity of n squared, as one loop iterates through each element, and the inner loop calculates the product for the remaining elements. In contrast, the optimized approach avoids nested loops by using prefix and suffix products, reducing the time complexity to n. Additionally, the naive approach would still require n space for storing the results, so the optimized solution achieves this improvement in time complexity without increasing the space complexity. This algorithm performs consistently across all scenarios, regardless of the input values. Whether the input array contains all positive numbers, all negative numbers, or a mix, the number of iterations and operations remains the same. As a result, the best, average, and worst-case time complexities are all n. To mathematically validate the time complexity, we note that both loops iterate through the input array linearly, performing constant time operations in each iteration. Since the loops are sequential and not nested, their complexities add up to n plus n, which simplifies to n. The space complexity is dominated by the output array, which requires n space, while the auxiliary variables contribute only 1. This efficient combination of time and space complexity makes the optimized solution a significant improvement over the naive approach, ensuring both correctness and scalability for larger inputs. When solving problems like product of array except self, there are several common mistakes you should avoid. First, using division without checking for zeros can lead to errors. While division might seem like a quick optimization, it becomes undefined if the array contains zeros. Always ensure you handle this case properly. Another frequent issue is modifying the input array directly. Many problems require the original array to remain unchanged, so it's important to use additional space if needed to maintain its integrity. Additionally, edge cases are often overlooked. Situations like arrays with only one element, all zeros, or identical elements can easily break your solution if not accounted for. Finally, using a brute force approach with nested loops might seem straightforward, but it results in an n squared time complexity, which is inefficient for larger inputs. It's essential to focus on optimizing your approach for better performance. Handling negative numbers is another challenge to be mindful of. If the array includes negatives, you must carefully manage sign changes, particularly when working with prefix or suffix products, to avoid introducing errors. From an interview perspective, there are key insights to keep in mind. Recognizing patterns like the use of prefix and suffix arrays is crucial, as they often unlock solutions with n time complexity. You should also pay close attention to constraints and edge cases, as interviewers frequently ask about these to test your problem-solving skills. For example, be ready to handle arrays with zeros, negative numbers, or very large values. Another important aspect is being able to articulate trade-offs. For instance, explain why using additional space for an O(n) solution might be preferable to an O(n²) brute force approach. Clear communication is key. Interviewers value your ability to explain your logic, edge case handling, and why your solution is optimal, even more than simply arriving at the correct answer. This problem is closely related to others that often appear in coding interviews. For instance, the product of array except self problem itself is a classic example, requiring you to compute an array where each element is the product of all other elements without using division. Another related problem is maximum subarray, which focuses on finding the subarray with the largest sum, a task that can also benefit from prefix and suffix techniques. Similarly, maximum product subarray challenges you to find the maximum product of a contiguous subarray, which demands careful handling of negative numbers. Lastly, trapping rainwater is another problem where prefix and suffix arrays come into play, as they help optimize the calculation of water trapped in an elevation map. Understanding these related problems and the techniques they share can help you build a stronger foundation for tackling similar challenges. There are several alternative approaches to solving the product of array except self problem. One common method involves using prefix and suffix products. Here, you build two arrays, one to store the product of all elements to the left of each index, and another for the products to the right. By combining these arrays, you can compute the result efficiently in O(n) time, though this approach does require additional space. If memory is a concern, you can use an optimized in-place calculation. This involves computing the prefix product during a forward traversal and storing it directly in the output array, followed by a reverse traversal to incorporate the suffix product without needing extra space. While this achieves both O(n) time and O(1) space, it can be harder to implement and debug under interview pressure. Lastly, there's always the brute force approach, where you calculate the product for each element by iterating through the array and skipping the current element. While simple to implement, this results in O(n² time complexity, making it impractical for larger inputs. Understanding these trade-offs is crucial when choosing the right approach for the problem at hand. Great job following along. To summarize, we tackled the product of array except self problem by using prefix and suffix arrays for an efficient O(n) solution. Remember, this problem is a fantastic exercise in optimizing solutions under constraints. Thank you for watching, and don't forget to like and subscribe for more tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!